Just letting a couple more people in. Okay, so before we continue our discussion of gases and gas exchange, I'm going to do a short recall question about one of the topics we covered on Monday. Okay. Ooh, where are we going? So on Monday, one of the topics we talked about are our lung volumes, our lung capacities, and some of the diseases that affect them. So we're looking at how we can identify whether we have an obstructive pulmonary disease or a restrictive pulmonary disease. If we're testing a patient, looking at their FRC and their FEVs. Okay, I'll give you another couple seconds and we'll go over this. Okay, so the answer should have been B, and we had like a 50-50 kind of split here. So when we're looking at obstructive versus restrictive diseases, we're thinking about the difference between diseases caused by increases in resistance, making it hard to breathe in, but also hard to breathe out, and diseases where we have lowered compliance. So we have a difficulty where our lungs are not able to fully expand. So we could identify these partially by looking at either a flow volume curve or this curve of volume over time. I'll note that with an obstructive disease, and it might be that you're getting a little flipped with these words, with an obstructive disease, that's the one that has to do with resistance, even though restrictive kind of sounds like resistance. Think about restrictive as being like, kind of like a cage around the lung, right? The cage being the lowered compliance, whereas the obstructive is like having something in your airway, that thing being a lot of resistance. So with an obstructive disease, we're going to end up having the same amount of volume in the lungs, but it's hard to get it out. So we're going to expire the volume more slowly. Versus in a restrictive disease, because the lung cannot fully expand with the pressure that we're creating with our respiratory muscles, we never get up to that full volume. So we're going to have a lower expired volume, even though over time at the beginning, at the very beginning of our breath, we'll see that we are breathing out at a good speed. It starts to taper off because we're not getting up to that same total volume. Okay. That said, we were talking about gases, and I think we ended on this slide last time. So we're talking about the fact that we can describe gases as having partial pressures. And the way we calculate a partial pressure is by taking our total pressure of the air, of all our gas mixture, and breaking that up into what proportion of that pressure is due to each gas. So to do that, we just multiply the total pressure for all our gases together by the percentage of that gas mixture that is the specific gas we're tracking. So we went through these calculations on Monday. So now we want to start thinking about the gas in the lungs specifically. So these were our calculations for gas in the atmosphere, which is made up of almost 80% nitrogen, 21% oxygen. Okay. But when we're looking at the gas in the lungs, we're going to see some differences. So our partial pressures in the lungs and in the alveoli are not going to be the same as our partial pressures in the external atmosphere. Okay, so one of the changes is going to be due to humidity. So here we have our calculations, not for the lungs. Well, yeah, here we have our calculations for humidity. So when we say humidity, what we're really saying is that there's a bunch of water vapor in the air. So if we have a bunch of water vapor in the air, our percentages are not going to remain the same as on that previous slide. At 100% humidity, so the most water vapor that we can get into the air, the partial pressure of water, so that's the water vapor, that gaseous water in the air, is 47 millimeters of mercury. Okay, so now that some of our pressure in the air is due to water vapor, our equation for the other gases changes. Because the fact that the air is humid doesn't mean that the air as a whole has more pressure. Our total pressure of the air at sea level is going to stay pretty much the same, whether that air is dry air or whether that air is humid air. So for that same total pressure, we're now going to divide it up into basically 3 big partial pressures. So we'll see if we compare, right? Now that we've put in this partial pressure of water, that water vapor at 47 millimeters of mercury, less of that total pressure is coming from nitrogen and oxygen. So comparing, right, before we calculated out for nitrogen, we had about 600 millimeters of mercury as our partial pressure of nitrogen. Now we're down to 563. For oxygen, we're also down, right? Before we had 160. Now we're down to 149. And here we've put on our partial pressure of carbon dioxide. And I think you can see why we didn't include it on the previous slide. There's really not much carbon dioxide. The partial pressure of carbon dioxide in the air is only 0.21 millimeters of mercury. Okay, so that's why we often leave it off, because it's not a significant contribution to the pressure of the air around us. Now that's not always going to be true in different situations like in our lungs. Okay. Oh, I think I said this at the beginning of the slide, but we're going to note that in the lungs, the air in our alveoli is going to be undergoing a similar thing, right? As we breathe in air and move it into the lungs, it gets humid as it passes through the conducting zone, as it moves into your body. So once we're in the alveoli, we are going to have to take into account this pressure of the water vapor. Okay. So another thing we want to understand as we're thinking about our partial pressures is not just the pressure of gas molecules in the gas volume, but also how we can think about the pressure of gas molecules dissolved in a liquid, which is kind of a funny concept. But as we track carbon dioxide and oxygen through our systemic circuit, we're going to be referring to the partial pressures of those gases rather than to the concentration or the number of moles of those gases. So it's important to kind of think about how this works. So when we're looking at these partial pressures of our gases in a liquid, it's going to depend on 2 things. So it is going to depend on the properties of that gas in its gas form, as well as the way that that gas interacts with the liquid. So we're going to see that the solubility of that gas in liquid in particular is going to make a difference for how we get from our partial pressure in the gas to our partial pressure in the liquid. Okay. So we're also going to keep in mind, because the reason we're talking about partial pressures in gas versus partial pressures in liquids is basically when we're in the lungs, right? We're going to be getting from our partial pressure of the gas in the alveoli, And we're going to be looking at how that influences how much oxygen basically goes into the blood and the capillaries, and how much carbon dioxide is coming out into that alveolar air out of the blood. So it's worth it to run through a kind of picture of this. Okay, we'll do an equation first. Okay, so the solubility of gases is regulated by something called Henry's law, which says that C equals Kp, where C is the concentration of the gas, K is a constant, and that constant is not a general constant for everything. That constant is a constant specifically for an individual gas, like say oxygen, at a specific temperature. So it's a constant, but it's specific to our specific situation and the specific gas we're tracking. Then P here is the partial pressure of the gas in the atmosphere. So I'm going to do a rearrangement of this equation because I don't like to have random equations that we don't know why we care about. So one of the things that we know with Henry's law is we're going to do some rearrangement here of this equation. So we start out with this equation that defines that the concentration of our dissolved gas in our liquid is going to be our constant. And that constant is also going to tell us something about the solubility of that gas. And it's kind of integrated into that number, times the partial pressure of the gas in the atmosphere in the environment that we're looking at. So we could rearrange this equation so that we are instead defining our constant in terms of these other factors, right? So if we flip this equation around, we could get to the fact that K equals the concentration divided by our pressure. Okay. And this is helpful for us because this is going to bring out a specific relationship kind of between the concentration and the pressure. So we get this constant if we divide our concentration by our pressure. We'll also note that you get that same constant, right? If you multiply both the concentration and the pressure by 2, right? If you divide 2 by 2, it equals 1, so it would make a difference here. So what we're going to see from this, or be able to recognize, basically, is that if we double the pressure in our gas, right, in our atmosphere or in our alveolus, we're going to get double the concentration in the liquid. And this is why we can refer to these pressures in the liquid and use them as kind of our measure of concentration, is because there's this direct relationship between the concentration and the pressure. We could directly calculate with this constant the concentration given just the pressure, and they're going to change in lockstep with each other. That's why we can do this. Okay, so we're going to get into some specific numbers for our gases that we're tracking, which are oxygen and carbon dioxide, right? Those are the things we care about. Okay, so for a given pressure, and we're going to pick 100 millimeters of mercury. So if we have 100 as our partial pressure in water, if that's our partial pressure, that's going to mean that we have 0.15 millimoles per liter of O2 in the water. But at that same partial pressure, we would have 3 millimoles per liter of carbon dioxide in water. So what this means, or what this is reflective of, is the fact that carbon dioxide is a lot more soluble than oxygen in water. So we're going to basically get a lot more carbon dioxide into the water for a given pressure. We get like more bang for our buck. And this is kind of good because we just looked at how much carbon dioxide we have in the environment, which was almost none. So it wouldn't really kind of add up and make sense how we have this transfer of carbon dioxide if this weren't the case. Okay, so we're gonna look at in pictures what this might look like. So here for our timestamp A, gonna grab my pen for us. Okay, so A here, this first image. we're looking at the start of a reaction, basically. So we're looking at what would happen if we start out at our first timestamp and we have a partial pressure of oxygen in our air of 100 millimeters of mercury. And at the start of the situation, when we set up this experiment, we don't have any oxygen in the water. So we have a partial pressure of oxygen of 0 when we start out. Over time, the partial pressure of oxygen and in the air versus in the water is going to reach equilibrium. So just like all the other pressures we've been looking at in this course, oxygen is going to flow down its pressure gradient. And in this case, we're talking about that pressure gradient as being this partial pressure of the oxygen. So if we have a partial pressure of oxygen of 100 in the air, that's pretty high, especially compared to this partial pressure of oxygen of 0 in the water, because there's no oxygen in there. So oxygen is going to flow towards where there's less oxygen. So it's going to flow into the water. Okay. So it's flowing into the water. And it's going to reach equilibrium at some point. And that point of equilibrium is defined by the pressure evening out rather than the specific number of moles of oxygen evening out, because this pressure is partially dependent on the solubility of oxygen in water. So once we reach equilibrium, we're going to see that we have this same partial pressure of oxygen in the air and in the water. All right. Okay. And if we compare this to the concentration, we'll see that essentially in this picture, right, we only had one of these O2 molecules go into solution, dissolve in the water. Okay. So it is the case that at this specific partial pressure of 100 millimeters of mercury in the air, that corresponds to 5.2 millimoles per liter. Because of the solubility of oxygen in water, that is the equivalent of only 0.15 millimoles per liter of oxygen in the water. So that's the equivalence here. And the reason we're looking at this image, and I've talked through it so much here, is because we want to compare this to the situation happening with carbon dioxide, which we know is more soluble in water. Okay, so that's our next slide. So here we're looking at carbon dioxide, and we've set up the same sort of experiment, right? We start out with carbon dioxide in our air, but not in our water. And we pick the same pressure, 100 millimeters of mercury, same partial pressure of carbon dioxide. So we let some time pass. We know that carbon dioxide is going to flow down its partial pressure gradient. So it's going to flow towards the water until the partial pressure in carbon dioxide is the same in the water as it is in the air. So here we can see they've reached equilibrium. Okay. Now when we are looking at oxygen, to reach this partial pressure of 100 millimeters of mercury, it only took one oxygen molecule going into the water to shoot up that partial pressure to 100. In this situation with carbon dioxide, it takes two here in this picture, right? So at that same partial pressure, we have more carbon dioxide in the water than we had oxygen. Note that, I'll flip back. Note that this is specific to the liquid, this aqueous environment, this water. So if we compare our concentration of O2 versus CO2, right, in the air at that partial pressure of 100, we have the same concentration, right, 5.2. But what's changed is the concentration in the water. So basically what this is partially pointing out to us is that we had that nice kind of additive relationship between our partial pressures in the air, where we were calculating out, you know, what percent of the air is nitrogen, what percent is oxygen, what does that mean for the partial pressures. We wouldn't be able to do that exact thing for water. Those equations would be specific to the gas form. With water, it gets more complicated. And it's dependent on those constants. It's dependent on the solubility. So what happens in water and therefore in blood is just a little different than what's going on in the air. But regardless, we're going to reach equilibrium, right? And this reaching equilibrium is going to be kind of the important thing to remember as we're moving through our next sort of set of slides. Okay, clear my scribbles. Okay, so what we really want to understand is the partial pressures in the alveoli and in the blood, and therefore how the gas, our oxygen and our carbon dioxide, is flowing through the lungs and then the cardiovascular system. So we're going to be looking at something called the oxygen cascade, which is basically this flow of oxygen. Okay. So we're going to have some steps where we're going to see gas exchange happening. So when we see gas exchange happening, we're going to expect our numbers for our partial pressures, which are reflective of concentrations, changing. So we're going to see gas exchange happening in the lungs themselves, right? That should come as no surprise, right? We've been talking about how much gas we're getting in the lungs, how much air we're getting in the lungs. We talked about how thin the walls of the alveoli are. We talked about how much surface area they have. We've been building up to the fact that we're having this gas exchange happening. Other place where having gas exchange is in the respiring tissue. So respiring, doing aerobic or respiration, right? So doing metabolism stuff. And we talked about that a little bit in our previous chapters where we were looking at oxygen getting oxygen uptake into the tissue and carbon dioxide flowing into the blood. And we're going to look at that a little more specifically, put some numbers on that now. Okay. And so we also kind of want to look at the determinants of the alveolar partial pressure of oxygen and the alveolar partial pressure of carbon dioxide, which is going to have to do with these two things, right? The gas exchange in the lungs, the gas exchange in the respiring tissue, and the gas concentrations in the atmosphere. Okay. So we covered gases diffuse down their pressure gradients. So those partial pressures, we're tracking them for a specific gas. We're not going to be trying to add together the partial pressure of the oxygen and the carbon dioxide to figure out which way they would flow. It's very simple. Oxygen is going to flow down the oxygen gradient. Carbon dioxide is going to flow down the carbon dioxide pressure gradient. Okay. Same thing is happening in the gas mixtures. We're going from high partial pressure to low partial pressure. They're diffusing down their own specific pressure gradients. So here's what we're talking about when we use this phrase oxygen cascade, right? We're looking at the flow of oxygen. So I'm going to grab my pen again. Okay. So up at the top here, I'm going to highlight some numbers for us. So some important things to know. We've talked a bit about the partial pressures of oxygen and carbon dioxide in the atmosphere, right? So about 160 for oxygen, lots of oxygen in the air, not very much carbon dioxide. So we have partial pressure of carbon dioxide of 0.3 here in the atmosphere. But what we haven't put specific numbers on are numbers in the alveolar air and in the blood. So in our alveolar air, we're going to see that our partial pressure of oxygen actually is 100. So we were choosing a convenient fake number for the last couple slides. Right, so our partial pressure of oxygen in the alveoli is a little lower, right, than our partial pressure of oxygen in the atmospheric air. And that's due to a couple of factors, right? So due to the fact that, right, so we remember that we have water vapor to account for, right? So we have humid air in the alveoli, water vapor. Maybe I'll put a title on this, right? reasons partial pressure differs in alveoli versus the atmosphere. Okay, so we got the fact that we have water vapor to account for. So that immediately is going to lower the partial pressure of all our other gases if we add in another gas. We also have the fact that we're mixing with dead air when we talked about our alveolar ventilation, right? We talked about the fact that when we breathe out, right, we know not all the air gets out of our lungs. So we have this mixing between the atmospheric air and the alveolar air. So we have mixing with dead air. And our third thing that we need to appreciate, let's say, is that gas exchange is happening the whole time we're breathing. It's a continuous process. It's not like you only do gas exchange when you've breathed all the way out or all the way in. It's happening the whole time. So we have continuous gas exchange. And this is important because I'm going to circle another set of numbers here, right? So we have the blood coming into the lungs here has a much lower partial pressure of oxygen, right? So we have a partial pressure of oxygen of 40 coming into the capillaries surrounding the alveoli. So the whole time, basically, right, we're going to be having continuous gas exchange. So we are continuously going to be moving some oxygen towards this low partial pressure of oxygen. So we're going to be bleeding oxygen into the blood, like basically the whole time. Okay, so all three of these factors are kind of going to bring down that partial pressure of oxygen in the alveoli. So if we continue the cascade, while we have the picture up, I'd like to do that, although it's written out in the slides later on. So this is what brings our oxygen down to 100. Okay. So then as the blood leaves the lungs, goes back to the heart, right, it's still 100. As it goes out to our system, right, there are systemic arteries, still 100. The next time we're going to see a change is the next time we have gas exchange, which is happening in the tissue. So the way we get from 100 to 40, right, we saw that our pulmonary arteries finally bringing blood to the lungs for oxygenation is 40. The way we fall down that gradient is because our tissues are actively respiring, right? So they're using oxygen in order to break down glucose. So they're uptaking a lot of oxygen. So this is where we have our concentration of oxygen fall. And then we just have that continue and get pulled back to the lungs, eventually leading to our pulmonary arteries. So that's what's going on with oxygen. And it's worth your time to trace through what's going on with the carbon dioxide as well. But it's basically just the reverse process. Okay. So the gas getting exchanged in the lungs, it's moving really fast. The diffusion between the alveoli and the blood is so rapid because we have this small diffusion barrier. Remember, we just have those type 1 alveolar cells. We have our endothelial layer of the capillaries, and they have a basement membrane between them. That's it, right? So just 2 cells plus a little bit of connective tissue, basically. Okay, so that's happening really fast. And the alveoli have a large surface area, right? They're these big sacs, right? These grape-like clusters on the ends of our bronchioles. So there's lots of places for this gas exchange to be happening, lots of walls. Okay. This means that actually if you were to look at the length of a capillary in the lungs, the gas exchange is happening in actually only the first third of the length of the capillary. So you basically have a lot more room for gas exchange to happen if for some reason it was happening slower, right? Which you might expect if the partial pressures of these gases in the atmospheric air, and therefore the stuff that's getting mixed into the alveoli changed. Okay. But what we can see, right, our full length of the capillary, right, so up to 100%, we're trying to get from the partial pressure of oxygen in our blood, in those pulmonary arteries, that deoxygenated blood coming into the lungs. We want to reach our full oxygenation of blood, which is normally a partial pressure of 100. Okay, so we can see that there's a really rapid rise, right? Nice sharp slope up here at the beginning from our venous blood. I say venous blood, this is the partial pressure in venous blood and in our pulmonary arteries. Remember that the pulmonary arteries are still deoxygenated. Okay. So we got up there really fast. So we have a lot more length of the capillary in case we needed some more time, but under normal conditions, we do not. This happens real quick. Okay. Conversely, same thing is happening with our carbon dioxide. So our carbon dioxide is at a partial pressure of 46 in our mixed venous blood. So in the venous blood that's coming back to the heart, we have a partial pressure of 46. Okay? So as we reach the lungs, this drops down to reach equilibrium, right? And that drops down specifically to a partial pressure of 40. Okay, so that is the partial pressure of carbon dioxide in our alveoli, and we again reach that in about a third the length of the capillary. And I actually am going to scroll back to our diagram of the cascade just so I can point out where that carbon dioxide part is happening, right? So we see carbon dioxide coming in at 46, right? It's getting to the lungs. We can compare alveolar air has a lot more carbon dioxide compared to the atmosphere. So alveolar air is at a partial pressure of 40 for carbon dioxide. So we reach equilibrium in a third of the length of the capillary, bringing the carbon dioxide concentration or partial pressure down to 40. Right, so it's traveling down its gradient, basically, right? Those extra 6 the 6th part of the partial pressure of carbon dioxide is going into the alveolar air to get expelled. And then we have that same partial pressure, 40 for carbon dioxide, traveling all the way through until we get to the respiring tissue, where it picks up some more carbon dioxide, bringing it to approximately 46. And we go round and round. Okay, so that's our carbon dioxide. So now we're going to talk about the gas exchange in the respiring tissue. So the gases are diffusing down their partial pressure gradients, which means that in the alveoli, our oxygen is dissolving into the blood, and our carbon dioxide is dissolving out of the blood into the air to get breathed out. And the opposite thing is going to be happening in the respiring tissue. So in our respiring tissue, our cells need O2. So they are going to be basically sucking up O2. And we can see the gradient here, right? So the usual partial pressure of the oxygen in those cells is less than 40 millimeters of mercury, or maybe equal to. But we know that the oxygenated blood coming in, right, reached equilibrium with the partial pressure of oxygen in the alveoli, which was 100. Okay. So we can see the gradient here, right? 100 is more than 40. So the oxygen is going to move into the tissue towards that lower number, towards that 40. It's why the oxygen goes into the cells, right? So oxygen is diffusing from the blood to the cells, and it's going to reach equilibrium here at the tissue just the way it did in the lungs. So it's going to bring down our partial pressure of oxygen to 40, which is why that's the partial pressure of oxygen in the systemic veins returning to the heart, and then in the pulmonary arteries going to the lungs. The opposite thing is happening with our carbon dioxide. So our respiring cells, they're producing carbon dioxide, and they have a partial pressure of 46 or even higher, potentially, right? Whereas the systemic arteries are bringing carbon dioxide in at 40 millimeters mercury as their partial pressure, right? Because that is the partial pressure of carbon dioxide in the alveoli. So carbon dioxide is going to move down its partial pressure gradient, which is the opposite of the partial pressure gradient for oxygen. So we're going to move from the cells to the blood. They're going to reach equilibrium, bringing the partial pressure of carbon dioxide up to 46. Okay. So this is the exact opposite of the process happening in the alveoli. We just have the same thing happening in the respiring tissue, but the gases are going the opposite direction. So in this case, instead of having gas going into the blood, instead of having oxygen going into the blood, oxygen is coming out of the blood and going into the cells, and the opposite for carbon dioxide. So you'll notice in a bunch of the diagrams and even on some of the slides, it's referring to mixed venous blood, which isn't a term we've encountered before. So what that means is basically like what these partial pressures would be if you measured them in, say, your inferior vena cava or something. So different tissues are going to be respiring at different rates, right? Different tissues are going to have different levels of metabolic activity. So these numbers might not be the same if you were measuring them in skeletal muscle, right, during or after exercise, right? So if we were to measure super locally for a very specific tissue, we might see some differences in these numbers. But as we return to the heart, the metabolically active tissue with the less metabolically active tissue, those blood flows are going to mix together. So what we've been tracing is the average number essentially in the body rather than the exact number for a specific type of tissue. This means that if you were to look at a specific vein, like a vein out in the arm versus a vein in the liver, you might also see different values for your partial pressure of oxygen and your partial pressure of carbon dioxide due to differences in metabolic activity of that tissue. So if you're out in some kind of local area and it's not a bunch of mixed blood, you would expect to see slightly different numbers. So when we say mixed venous blood, it's an average, and it's basically measuring that blood coming back to the heart after we've kind of averaged together the activity of all the tissues. Okay, so remember that our systemic veins, right, they come to the right atrium. We've been seeing this in lab this week, which is pretty cool. For those of you who haven't had anatomy lab yet, we're getting to play with hearts. It's super fun. Okay, so we have our systemic venous blood returning by the superior and inferior vena cava to the right atrium, traveling through the AV valve into the right ventricle, then getting pumped out through the pulmonary trunk into the pulmonary arteries, going to the lungs. All of that is deoxygenated blood. Then we have the gas exchange happening in the lungs. So it's not until we get to the pulmonary veins that we would be up to those numbers after exchange. So in the pulmonary artery, and only the pulmonary artery of all the arteries, we're going to see the same values as for mixed venous blood. Okay. So the blood in the pulmonary artery is still deoxygenated, so its pressure, partial pressure of oxygen, will be at 40 millimeters of mercury. If we move to the pulmonary veins, which are then bringing oxygenated blood back to the left side of the heart to get pumped out to your system, that's where we would see the partial pressure of oxygen up to 100 millimeters of mercury. And for carbon dioxide, in the pulmonary artery, so the pulmonary trunk and then the pulmonary arteries, we got same thing, deoxygenated blood. So we're at 46. As we return with our oxygenated blood in the pulmonary veins, that would be down to 40 for the carbon dioxide. So there's a lot of text at the bottom here, but note that this whole section I already wrote out for us on a previous slide while we were looking at a diagram. Okay, so don't freak out that you have too much to put in your notes. You've seen that already. Okay, so the factors that are affecting our alveolar partial pressures are in part the partial pressures in the inspired air, so in the atmosphere. Then we're going to have to take into account the minute alveolar ventilation, which we may or may not remember from Monday, but minute alveolar ventilation, when we're talking about minute ventilation, we're basically talking about how much air gets into the alveoli per minute. And so our equation for minute alveolar ventilation, I'm going to put ventilation A for alveoli, remember, is our tidal volume, VT, times our respiration rate, not TV, VT, times our respiration rate, so how many breaths we're breathing in a minute. So this quantity, this first one is our minute ventilation, but we want our minute alveolar ventilation, which is a little more specific. So we got to remember that we're removing all the dead air here. All right, so same thing, our dead space volume times our respiration rate. Okay. So this is basically telling us how much fresh air we're getting into the alveoli, so that matters when we're thinking about what our alveolar partial pressures of oxygen and carbon dioxide are going to be. And it also matters the rate of respiration happening in the tissues, because they're the ones that are using oxygen and carbon dioxide. So if we end up with slightly different constant partial pressures of oxygen and carbon dioxide in the blood than normal, than in that normal oxygen cascade we ran through, we're going to have different amounts of gas exchange, potentially reaching different equilibrium states. The biggest factor here of the ones that are affecting our alveolar partial pressure, though, really is our alveolar ventilation. So this is really the big thing, right? So it's not the same as atmospheric pressure because we have some other considerations, but really what determines the majority of how much oxygen we have in our lungs is how much fresh air we're getting in there. So we have some changes to the numbers because of these other factors, but if we weren't getting fresh air, we would deplete our oxygen. Okay. So here we have some vocab words, super useful vocab words for situations you might see in a clinic. So when we're talking about our ventilation and our alveolar partial pressures of these gases, we will sometimes, and often, right, we're interested in whether our ventilation, so the amount of air we're breathing in, and specifically the amount of fresh oxygenated air reaching those alveoli, we want to know whether it's enough for your tissues to get everything they need, for them to get enough oxygen to do their job, and for them to be able to effectively get rid of their waste product, carbon dioxide. As we move into our next packet, we're going to see that the carbon dioxide bit is important because it also has effects on blood pH. So that's also a very important factor, although we haven't focused that much on why exactly getting rid of waste products is important yet. Okay. So this first term, hyperpnea, refers to the fact that sometimes we're going to see increased ventilation. So we're going to see more air getting into the lungs, getting into those alveoli. But it's normal and good because it's due to increased demand, right? So if you have hyperpnea, like you're breathing fast, right? If it's because you just went on a run, right? You have an increased demand for oxygen, that's fine and normal. And this means that while you have increased ventilation, so while you have increased air getting into those alveoli, if you were to look at the partial pressure of oxygen or carbon dioxide in the blood, it wouldn't be that different than the normal state. The reason being that all that extra air that you're breathing in is getting used up by the tissue. This differs from our second two terms, which are actual problems. So hypoventilation and hyperventilation means we're getting the wrong amount of these gases. So in hypoventilation, remember hypo refers to something being low. So in hypoventilation, this means you don't meet the demands of tissue. And the reason for that is that you do not have enough oxygen in the blood, right? You're breathing potentially really slowly, potentially really shallowly, right? So we're going to see that the amount of oxygen in your arteries is decreasing. So if we were to take an exact measurement, a decrease would be anything less than 100. This means that because you're not breathing enough, you also are not getting rid of your waste product, carbon dioxide, fast enough, which means that we're going to see our arterial pressure of carbon dioxide increasing. So in the arteries specifically, it would be above 40, right? Because we're not getting enough of that carbon dioxide out in the alveoli because we're not breathing enough to maintain the appropriate partial pressure of carbon dioxide or oxygen in the alveolar air. So the opposite of this is hyperventilation, right? So hyperventilation, right? You're breathing really fast, maybe you're kind of panicky, right? Your ventilation is exceeding the actual physiological demands of the tissue, right? So this is gonna result in the opposite situation. So you're getting a lot of fresh air because you're breathing super fast, right? So your arterial partial pressure of oxygen would increase. Your arterial partial pressure of carbon dioxide would decrease. So you're really super saturating your blood with oxygen and depleting it of carbon dioxide. Which brings us to the transport of gases in the blood. Since we are running a little behind according to our schedule, I'm going to try to get through like one slide of this, but we'll pick up with this stuff on Monday mostly. Okay. So after we get oxygen and carbon dioxide into the blood, we are interested in how they're moving around. And thus far, we've just been talking about like partial pressures. Really, we've been talking about stuff dissolving in the plasma. But we remember that we have these special molecules in our red blood cells, right? We have hemoglobin there specifically for carrying a bunch of oxygen. So we're going to have to account for some other factors when we're thinking about how exactly we're getting oxygen to the tissue. Okay. So this is kind of a caveat to the entire previous PowerPoint. So oxygen gets transported by hemoglobin. Oxygen, as we saw, it has low solubility in water, which means it's not very soluble in the plasma either. So when we are looking at oxygen in the blood, very little of it is actually dissolved in the plasma. Remember, the plasma, right, is basically the fluid around all our blood cells. So only 1.5% of arterial blood is in the plasma, and the rest of it is going to be in hemoglobin. So hemoglobin is this protein with 4 subunits that we find in our erythrocytes, so in our red blood cells. Oxygen binds to hemoglobin, and it binds to hemoglobin reversibly. So we have this equation at the bottom. We can take hemoglobin floating around in the blood. We can take oxygen floating around in the blood, combine them, bind the hemoglobin on. But hemoglobin can also jump off, oxygen can also jump off the hemoglobin and go the opposite direction. So if we have hemoglobin with no oxygen bound to it, we call it deoxyhemoglobin. If they are bound together, we call it oxyhemoglobin. So that's just some terminology that we'll be using when we dive into this next week and think about how oxygen binds to hemoglobin and what influences how much oxygen binds to hemoglobin. Okay, So we'll leave it there and we'll pick up here on Monday. Have a great weekend, everyone.
Thank you. You too.
Will there be a quiz on Monday?